Hi, in this video we are going to talk about mathematical measures of central tendency. We define central tendency as a descriptive summary of a data set through a single value that reflects the nature of the entire data. We notice that there are 5 central tendencies that we are going to discuss in this session, and there are 3 mathematical central tendencies: arithmetic, geometric, and harmonic mean. And then there are median and mode, which are positional central tendencies. In this video, we're going to talk about mathematical central tendencies, and we'll start our discussion with arithmetic mean. Arithmetic mean is defined as the sum of all observations in a data series divided by the count of all observations in that series. Whoa, too many English words. And the problem with English is that it's less precise. And that's why we mathematicians developed our own language, and it's called mathematics. And that language is more precise and concise, that is, shorter than English. Let's read the same definition translated to mathematics. Arithmetic mean denoted by x bar. We are going to give it a notation of n observations x1, x2, etc. xn. So there are n observations is given by x bar is equal to x1 plus etc plus xn divided by n. If you notice, these two are the same. Sum of all observations. Here the observations are x1, x2, etc. xn. On numerator we have x1, x2, etc. plus xn divided by count of all observations. Here the count of all observations is n, because there are n observations, so divided by n. So these two are basically the same. And let me tell you a little secret, that mathematicians are very lazy. Don't tell anyone though. If you notice, here we have written some Greek. I said Greek intentionally because there are some Greek letters here. This symbol is capital sigma in Greek. And here in this particular case, we will read this as summation I is equal to 1 to n. That is, I is running from 1 to n. I becomes 1, 2, 3, and so on. Xi. What this means is, first you put I is equal to 1, you have x1. Add I, put I is equal to 2, you get x2. And add, put I is equal to 3, you have x3 plus etc. And your counter stops at n. So you have, adding it up, you have xn. So this particular term is nothing but the numerator here, and the denominator is kept as such here. So this is just the same formula in a more concise way. This is the power of mathematics. Look at a lot of words in English in the previous definition has reduced to this one simple line in mathematics. Now, mathematics is about solving problems, and it develops your problem solving skills. But some teachers would always tell you that mathematics isn't about memorization. That's right. Do not memorize any of the problems, but every subject, be it psychology or mathematics, has a component of memorization. And in this case, out of 20 or 25 slides that I'm going to present you today, there are 4 lines you should memorize. And one of those 4 lines is this particular formula. So, why should we memorize? It's useful for us. Suppose we don't have access to any books or internet, and all of a sudden you have to do some math about your research work. Simple formula will always be there to help you out. Let's continue our discussion. And before we do examples, I'll tell you how to calculate arithmetic mean. Arithmetic mean defined by x bar is equal to, first step in calculating is identifying the number of observations n. Second step is adding all those numbers, adding all those observations together. And in the third step, you have to divide the result by n. Let's do a simple example problem. We have to find the arithmetic mean of 1, 3, 5, 7, and 9. If you notice, the first step was identifying the number of observations, and in this particular case you have 1, 2, 3, 4, 5. There are 5 observations. And then add up all our observations, that is 1 plus 3 plus 5 plus 9. Oh, I missed 7. 7 plus 9, and that's 25. Next step, divide the sum by n. Here 25 and n is 5, and thereby the mean is 5. Easy. If you notice, the arithmetic mean we got is a number in the distribution. That need not be the case always. Sometimes it may be 5.1 or 5.2. And if you notice, this is interesting. There are two numbers to the left and there are two numbers to the right, and this particular number seems to be at the center of this entire set of numbers. It doesn't tell us how wide this distribution is, or saying what is the maximum number or minimum number or any of those information. It doesn't tell us any of those informations, but it gives us a arithmetic mean as a representative for the entire distribution. We have got a number which is towards the center of this entire distribution, if you notice. Just like just like how a central tendency should be. Let's look at another example. This time I'm going to increase the number of numbers. A big list, right? Before we calculate, let's make some observations. 1. By applying the formula, we know this is what we get. We can add up all the observations divided by, here if you count the number of data points in this distribution, you'll find that it's 18. So divided by the number of observations. I'm going to rewrite the same thing using something we learned in first or second standard, that 2 plus 2 plus 2 plus 2 is equal to 4 into 2. Simple, right? So how are we using it? If you notice, there is only one 1, so I put 1 into 1. There are 1, 2, 3, 4 2's, so I put 4 into 2. And like that, I grouped all the 3's, 4's, 5, 6, and 7 separately. This is more neater and concise, right? And in fact, this is the number of ones in the series, and I'll call it the frequency of 1, and this is a frequency of 2, and 1 is the first data point, let me call it x1. 2 is the second data point, so let me call it x2. And this is f3, frequency of 3 into x3, and so on. F 7th data point into x7. Interesting. So we have written the same information we have in a more neater way. Can we use this to write our distribution itself in a more neater way? Turns out we can. Going forward, if you notice this distribution, just like we did earlier, there are 7 numbers, 1, 2, 3, 4, 5, 6, and 7. And hence I have written down the numbers in the first row, and 1 appears once, 2 appears 4 times, 3 appears thrice, and so on. So I've simply written down the frequency of each number in the entire distribution. So instead of listing 18 numbers, we could summarize the entire table with 8 columns. Interesting. This becomes especially useful. Suppose you are collecting reviews of a movie, and users or those who are responding to your survey were asked to rate the movie in a scale of 5. That is 1, 2, 3, 4, 5. They can give any one of the ratings. And turns out you gave the survey to 100 people who attended a show. So you have 100 people who have rated the movie with a number between 1 and 5. If you try to list all the responses, you have 100 responses with you. Instead of that, if you use a table like this, you can count the number of people who rated the movie 1, you can count the number of people who rated the movie 2, and so on. So your entire data can be presented more neatly using frequency table with simply 6 columns. So that's one of the advantages. We are writing the data neatly. Now, when the distribution is given in frequency table, we need some modification to our arithmetic mean formula. Earlier, we observed that this entire equation can be rewritten as frequency of a number into that number plus frequency of second number into the second number, and so on until frequency of nth number into xn. So taking inspiration from this, we will rewrite the definition of arithmetic mean as arithmetic mean x bar of n observations xi, and each xi has frequency fi, that is x1 has frequency f1, and so on, will be equal to f1 into x1 plus f2 into x2 plus etc plus fn into xn divided by f1 plus f2 plus etc fn. Hey, I agree with the numerator, but what about denominator? f1 plus f2 plus fn? But earlier we had total number of observations in the denominator, right? Let's check it out. Let's try see what is f1 plus f2 plus etc plus fn. f1 is 1 plus 4 5 plus 3 8 plus 3 11 plus 2 13, 13 plus 3 is 16, 16 plus 2 is 18. Whoa! Turns out the sum of frequencies is nothing but the total number of observations. So the denominator also agrees. The numerator agrees, the denominator agrees, and turns out this formula is simply the earlier formula in a more neater way. And as I told you, mathematicians are lazy, therefore we write it in terms of summation as summation fx divided by summation f. This is the second formula in this entire video that you'll have to by heart. So please memorize this formula. Let's go ahead and apply it in a example. This is the same example that we were discussing earlier. This time I have given it in frequency table. How do we go about it? The formula is given by x bar is equal to summation fx divided by summation f. To calculate this formula, we need to find summation fx. So we need to find f into x in each case, and we need to add the result up. I know it can be done manually by writing x1 into f1 is equal to x2 into f2 is equal to, and so on. But that's a bit tedious process, right? So let's use a little shortcut and simplify the entire process by using a table. In this particular table, in the first column I have simply copied the values of x. In the second column I have simply copied the values of frequency, and in the third column I have just multiplied the frequency with the value of x. So let's fill in the table first. 1 into 1 is 1, 2 into 4 is, that is frequency into corresponding value of x is 8, and 3 into 3 is 9, 4 into 3 is 12, 5 into 2 is 10, 6 into 3 is 18, 7 into 2 is 14. And now summation fx can be found by simply adding the third column. The denominator summation f can be found by adding the second column. That simplifies our job and calculation a lot easier, right? Makes it a lot easier, right? Let's add this up. 1 plus 8 is 9 plus 8 is 9, 9 plus 9 is 18, 18 plus 12 is 30, 30 plus 10 is 40, 40 plus 18 is 58, 58 plus 14 is 72. Adding up the frequency, you will get 1 plus 4 is 5 plus 3 plus 3 is 11 plus 2 is 13 plus 3 is 8, 16, 16 plus 2 is 18. So turns out we have now easily found the numerator, that is summation fx is 72 divided by summation f is 18, and the answer is 4. So this is one way. This is finding the arithmetic mean when a frequency. This is how to find the arithmetic mean when a frequency table is given. Let's look at what to do when we have a class interval in our frequency table. How we do go about it is, we'll again draw a table and add one more column, and that column just takes the mid value of x. That is, our first interval is 0 to 10 and mid value is 5. 10 to 20, mid value is 15. 20 to 30, mid value is 25. Now we will treat that as our x. So f into x is 10, 3 into 15 is 45, 2 into 25 is 50. To find summation fx, you have 10 plus 45, 55 plus 50, 105. And summation f is 2 plus 3, 5 plus 2 is 7. So applying it in the formula, you have 105 divided by 7. That is equal to 50. So in case of class intervals, find the mid value and then use that as your x to find the arithmetic mean. But there is some trouble. The first trouble is, here it is from 0 to 10. What if it is all the numbers less than 10 instead of 0 to 10? You cannot find the mid value. So in that case, we won't be able to find the arithmetic mean. Before we conclude our discussion on arithmetic mean, let's do some experiments. Have you done experiments in mathematics before? They do it in physics and chemistry, right? You know about that crazy scientist who thought there are two things in the test tube, what could possibly happen? He just mixed it up and it exploded. I'm talking about Alfred Nobel, the person who accidentally found the explosive called TNT. So is experiments in mathematics that dangerous? Will it explode? We don't know. Let's see. Oh, wait. We are not supposed to find the arithmetic mean. Turns out arithmetic mean is given as 12.4 for this frequency distribution. Find summation f into x minus x bar. Oh, we have to find a summation of frequency into x minus x bar. Let's use the same trick we used earlier. Let's draw a table with value of x in the first column, value of f in the second column, and next thing we have to find is x minus x bar. So let's put that in the third column, and product of f and x minus x bar in the fourth column. So let's start. X bar is 12.4, 8 minus 12.4 is 4.4. Wait, 12.4 is bigger than 8, hence there will be a negative sign. 12 minus 12.4 is 0.4. 14 minus 12.4 is 1.6. 16 minus 12.4 is 3.6. Now, multiplying with the frequency, you have 1 into minus 4.4, 4.4, 1 into 0.4, minus 0.4, 3 into 1.6, you have 4.8, and 0 into 3.6, you have 0. Now, to find f into x minus x bar, we simply have to add up this particular column. Minus 4.4 minus 0.4 is minus 4.8, plus 4.8, we have 0. Interesting. For this particular distribution, turns out f into x minus x bar, when we add it up, it is equal to 0. It's not just true for this particular distribution. It's true for any distribution. That is, for any distribution, sum f into x minus x bar is 0. Or more mathematically, summation I is equal to 1 to n fi x minus x bar is equal to 0. Interesting. It didn't explode. That's the first point to be noted. 2. By doing an experiment, we found some interesting results. Let's do another experiment. This time, let's find the arithmetic mean of 2 and 3. Arithmetic mean of 2 and 3 is 2 plus 3 by 2, that is 2.5. That is 5 by 2 and 2.5. Going forward, find the arithmetic mean of 4 to 1. I wonder where we are heading to. Anyway, we are asked to do it. Let's do it. 4 plus 2 plus 1 by 3 is equal to 7 by 3, and the value is somewhere around 2.33. So let me conclude and write the final value, 2.33. Oh, find the arithmetic mean of 2, 3, 4, 2, 1. Hey, interesting. 2, 3, 2, 3, 4 to 1 and 4 to 1. Anyway, they have asked us to find the arithmetic mean. So let's simply find it. 2 plus 3 plus 4 plus 2 plus 1 divided by 5 is equal to 12 by 5 is equal to 2.4. But since we are mixing up these two distributions, would this 2.4 be would the arithmetic mean of this bigger distribution be equal to arithmetic mean of these two arithmetic means? Let's try find the mean of 2.3 and 2.33 divided by 2, and turns out that is equal to 2.4166. Oh, the 6 is never ending. So the arithmetic mean of the combined distribution is not equal to the arithmetic mean of means. In fact, if you continue your experiments like this, you will come at make an observation that if x bar is the arithmetic mean of n observations x1 to xn, y bar is the arithmetic mean of n observations y1 to ym, then the arithmetic mean of combined distribution, where there will be m plus n observations, will be equal to nx bar plus my bar divided by m plus n. This is a very handy formula, especially in puzzles for different entrance examinations. You will see this idea popping up. So it's good to learn this small trick. Anyway, we found it by experimenting, and anything found by experimenting is fun to learn. Going forward, is arithmetic mean ideal? It is rigidly defined. We already noticed that even if we calculate arithmetic mean of the same distribution using different formulas, it will give us the same answer. So it's rigidly defined. Oh, need not say it's easy to understand and calculate. It's based on all the observations because in numerator we are adding up all the observations. Hence, it's based on all the observations. It's suitable for further mathematical treatment without any question. In fact, this is the most suitable mean among all the central tendencies to find for further mathematical treatment. You'll see why soon. It is affected as little as possible by fluctuations in sampling. Yes, that's also true because we are considering all the observations for our calculation. The last one, it is affected by extreme observations. The thing is, suppose you are finding arithmetic mean of 1, 2, 3, 4, and 100. When you find the arithmetic mean, you'll see that it lies somewhere around too far away. I think it will be greater than 20. The x bar will be greater than 20. But majority of our values lie near 1, 2, 3, and 4. So it is affected by extreme observations. Extreme observations can give you a little absurd results. So that's the only weakness of arithmetic mean. Otherwise, it would have been the most ideal mean of all. So our final score for arithmetic mean is 5 out of 6. That's not the only accusation against arithmetic mean. As we already observed, nominal and ordinal data, we won't be able to find the arithmetic mean. We cannot determine it by inspection or graphically. And the third case against arithmetic mean is that it cannot be calculated for distributions with open-ended class. So we noticed that earlier when we were doing a similar problem. With score 5 out of 6, arithmetic mean is now going to compete with the other two mathematical central tendencies, geometric mean and harmonic mean. Geometric mean of a distribution with n observations x1 to xn is given by nth root of its products. By nth root, what I mean is root of, you know what this is, square root of a number a is given by a to the power 1 by 2. And cube root is written as a to the power 1 by 3. Like that, if there are n observations, we find nth root of the product of those observations. So by hearing it itself, it sounds a bit crazy, right? Let's see, we'll try some problems. Then harmonic mean is given by just flipping everything. It's like arithmetic mean with everything upside down. 1 by n into, flip the first observation, 1 by x1 plus 1 by x2 plus etc. plus 1 by xn. And in more beautiful mathematical way, you write it as 1 by n into summation 1 by x. Let's try some problems and see how useful these two means are. First, let's find the geometric mean and harmonic mean of this distribution. I have chosen a smaller number 3 because for geometric mean you have to find nth root. So g is equal to 2 into 4 into 8 to the power, there are three numbers, so 1 by 3. And this will be equal to 4. You can use a calculator or you can use the trick that this is 2 into 2 square into 2 to the power 3. And the entire thing reduces to 1 plus 2 plus 3, 6, 2 to the power 6. And 2 to the power 6 to the power 1 by 3 is equal to 2 to the power 6 by 3 is equal to 2 square. And that's 4. That's how I found, but you can use a calculator if you want. Harmonic mean is given by h is equal to 1 by 3 into invert the first observation, invert the second observation, plus invert the third observation. This is equal to 1 by 1 by 3 into 7 by 8. And 1 by something is equal something else is equal to something else by something. Hence 3 into 8 by 7, this is equal to 24 by 7. 24 by 7 will be somewhere around 3.9. And geometric mean is equal to 4. So if you notice, this is talking about something towards the center. The numbers are towards the center of this particular distribution. So it's giving us some useful insights. Going forward, let's find the geometric mean and harmonic mean of this particular distribution. First of all, there are 4 observations. So G is equal to minus 1 into 2 into 2 into 4 to the power 1 by 4. There's a small trouble here. We know that root of minus 1 itself is a trouble. We don't know the value. We mathematicians call it very imaginary thing called I, but for the rest of the world, this is not real. This is not real. This is not possible to find root of minus 1. So talk about finding the fourth root of a negative number. We cannot find geometric mean in this case. Harmonic mean is equal to 1 by 4 into minus 1, 1 by minus 1, which I'm writing as minus 1, 1 by 2 plus 1 by 2 plus 1 by 4. Here, if you notice, minus 1 plus 1 is equal to 0. So you have 1 by 4 into 1 by 4 is equal to 1 by 16 is equal to 16. Oh, that's not sensible. Given this particular distribution, 16 is too far away. So this is one of the places where harmonic mean and geometric mean are failing us. Let's try this. This should be easy. There are no negative numbers. G is equal to 0 into 2 into 4 is c to the power 1 by 3. Hey, there is a 0, so it should be 0 to the power 1 by 3 is equal to 0. When there is a 0, geometric mean will 0 in the distribution, geometric mean will always be 0. Let's try to find harmonic mean. H is equal to 1 by 3 into 1 by 0. Oh no, I'll tell you a little secret. We mathematicians are scared of 1 by 0. Some of you may say this is equal to infinity, but that's not the case for us mathematicians. Sometimes for the sake of calculations, we take it as infinity. But for us mathematicians, 1 by 0 is not defined. And we mathematicians who are very careful about precision, we don't have too many things undefined, except for things like division by 0. Hence, we are little scared of it. And when there is 1 by 0, we simply say, we can't calculate harmonic mean in this case. Interesting. So we saw 3 distributions, out of which 1, geometric mean and harmonic mean gave us good insights. But in the second case, geometric mean, we couldn't find geometric mean. Harmonic mean, which we found, was not helpful. 3, geometric mean became 0 and harmonic mean couldn't be found. So let's look at how ideal geometric and harmonic mean is. Arithmetic mean had 5 out of 6 points. What about geometric mean? Rigidly defined? Of course, we have a mathematical formula for it. Anything with mathematical formula is rigidly defined as well as useful for further mathematical treatment. Easy to understand and calculate? You be the judge. Based on all observations, very much. We are using all the observations. In geometric mean, we are multiplying them all. In harmonic mean, we are inverting them and adding them up. So it's based on all observations. Fluctuations of sampling. Oh, no matter how it fluctuates, if there is a zero, geometric mean fails you. If there is a negative number, geometric mean fails you. Extreme observations. Turns out these two guys won't play nice with them. So geometric mean and harmonic mean got a score of 3 out of 6. Arithmetic mean is the closest to the ideal central tendency we can have. And in fact, in the future mathematical treatment or in the future videos, you will notice that arithmetic mean is the most useful central tendency for further mathematical treatment. And we also made some observations about geometric and harmonic mean. When there is a zero, both of them give trouble. When there is negative number, both of them give trouble. And they cannot be calculated for distributions with open-end class like arithmetic mean. So we will conclude our discussion on mathematical central tendencies. And if you notice, arithmetic mean was more ideal than geometric and harmonic mean. Does that mean we should use arithmetic mean always? Not exactly. There are places where geometric mean and harmonic mean will be more useful than arithmetic mean. For example, if our numbers are all upside down, that is, fractions, harmonic mean may be easier to calculate and more insightful. And then cases like finding the average time of travel up and down, the other two, that is geometric mean and harmonic mean, may be more insightful, maybe giving you a more better number summarizing the nature of the distribution. With that small note, I'll wind up this video. Thank you.